All right, so let's get started. So page 1. And this would be chapter 1. All right, and the title is Vibration of a single degree of freedom systems. All right. So many times, probably on the notes, you will see the acronym SDOF. That's basically would be the abbreviation for single degree of freedom. Okay, so at the beginning of this chapter, really I'm going to start with what I think is the most important part of this, okay, of these renal vibrations, and it's the part that is generally the most overlooked, because to solve, basically vibration is to solve one differential equation, okay? And to solve a differential equation, once you know how to solve it, you always solve it the same way, okay? And it's not that difficult, okay? It's not that difficult. But what is difficult to get is to get the actual differential equation that is actually representing the problem that you want to solve, okay? So, because you can be the best person solving differential equations, if you are not solving the equation that is actually representing your problem, becomes useless, no? Okay? So the first part is a little bit like how to show you to derive the equations, even though most of the class is just about how to learn how to actually derive the solution and understand the solution of the differential equation. All right? Okay, so let's do over here. So the first section in this chapter will be differential equation. But basically, really, this should be equivalent here to what I'll probably refer more commonly as equation of motion. That is a differential equation. Okay, so really here what I want to emphasize is that the equation of motion is a differential equation. Okay, all right, so for a spring, mass oscillator. So what does that mean? So if we have a spring, so let's first do the mass. This would be the mass M. All right. Now we need a spring. Okay. Let's say this spring will be attached to the wall, and let's say this is lighting on the surface. Okay. So every time we're going to derive any type of equation, we need to have a reference frame. Okay. So over here, let's say our reference frame will be locate at the CG, and it will be just, this is just moving in, this can only move in one direction, correct? So what do we call this chapter? Single degree of freedom. The degree of freedom refers basically to the type of motion you can have. So what type of motion can this block have? It can only move in one direction. So that's 1 degree of freedom motion, no? If this could slide in that direction and then let's say rotate, that would be 2 degrees of freedom, correct? Unless actually you can relate one to the other, but all right. So over here we have K is the spring, M is the mass. All right, and over here I'm gonna add one little thing just to be detailed. Let's say the spring K is unstretched at t equals 0. Okay, so what type of problem is this actually modeling over here? So what's going to happen over here? Let's say if you pull on this little mass and let go, what's going to happen? This is going to start oxidating. Or if you compress it and let it go, it's going to start to oxidate. Okay, and if it was no friction on over here, this could go theoretically forever. No? Okay. All right, so I'm gonna show you 2 different ways to derive the equation of motion. Really, only one is necessary at the beginning, but the second method is, if you want, makes this problem more complicated, but makes complicated problem a lot easier. Okay, so what's it? Okay, so the first thing we need to do now is to derive the equation of motion. Okay, so we're going to do it in 2 different ways. So first approach, which is the one you know, and personally I think it's the best because it's no assumptions, you get all the information. It's basically using Newton's law. So motion of force equals to ma. So here just a reminder, maybe. So motion of forces equals to ma, and then you have the other one, which actually there's only one. Newton's law is that one, but sometimes you also learn this one here, which is I alpha. And the reason why I'm putting both of them is just to indicate something. In general, this one will take care of what type of motion? The translation, and this one will take care of the rotation. Okay? If you probably learned from dynamics that an object can either move in translation or in rotation, and if the object has actually both motions, translation and rotation, you can actually break it. You can actually break the motion of that object into the 2 components, the translational and the rotational. No? Okay. Right. So just using this one. So what is the general procedure? So it will be like always, will be 1. See if I have a different color here. No. So let me do it in green. 1. Same as every other class. The most important part is to do a figure, draw a figure or sketch of the problem. I don't like to call it, I mean, I'm going to call it here, but I don't like to call it free body diagram because free body diagram relates to statics, not moving, no? But this is actually moving, so but I mean, some type of figure, that's the important part. So now, what do you need? Some type of figure, because from the figure, you're going to define the problem, you're going to define the coordinate system. And once you have the coordinate system, what can you do? You can apply Newton's second law. Okay? So this will give you a differential equation. And then the last step in the program will be what? What is this class really about? 3 will be to solve the differential equation. Okay? But at this step, let's just keep it over here. Okay, so let's try to solve this problem here following this method over here. All right? Okay, so step 1 is to do some type of figure. So over here, this is the way I teach it in dynamics. So I'm going to do the same thing over here. All right, so remember, this is the problem we are solving. All right, so I'm just going to sketch the mass over here. All right, so I sketch one mass over here. And now, since we use the equation here, summation of forces equals to MA, the left-hand side refers to the forces acting on the mass. Okay, actually, this is the external forces. And MA refers to the inertia effects that are induced by the motion. Okay, so that's why I like to do 2. So for example, I do over here. If you want, generally I don't do this, but basically this sketch over here would be for the summation of forces, and this one will be for the inertia effects. All right, so let's see. If we assume no friction, all right, what would be the forces acting on the block over here of mass M? You could have, you will have the weight, mg. You will have the normal reaction, okay? And then what will you have? Let's say initially we move the mass to the right. So what will happen? The spring will create a force going to the left, all right? So we'll have over here, force of the spring equal kx. Okay, and we assume no friction. All right, and now what will be the inertia effect? Okay, what is the only way that this is going to move? It can only move right and left, no? So if we have here a term, that would be MA. Okay, now maybe I'm forgetting here the most important part, which should be what? We need to define a current system. Okay, so it doesn't matter from where you create it, but since you have the object, let's say I'm going to create it from the CG over here. This would be the current system, okay? So now, step 2, we need to apply Newton's second law. So what type of motion is this object going to have? Obviously, it's only going to move in translation. So if it's only moving in translation, what should be the equation defining the motion? Summation of forces equals to MA. All right? We come over here, we say summation of forces equals to MA. And every time you write one equation, the equation doesn't come from magic. It needs to come from a figure, a free body diagram. All right? So over here, the motion is only in one direction, only on the x direction. So really, what should be the motion of the y direction? 0, no? What should be the motion? The lateral motion should be 0. So here we're just interested on we notice that the motion is only in x direction. So in this case, we're just going to apply this equation here. Summation of force equals to MA on the x direction. Okay, so if we look at the diagram, everything should be on the figure. What are the forces acting on the x direction? On the left-hand side, the only force acting would be, so maybe let me just rewrite that equation here. Summation of forces equals to MA will give what? Kx is going on the negative direction. All right, so we have minus Kx. Now, so this comes from the left-hand side. Now, what are the inertia effects? Will be MA. Okay? And now I'm just going to write over here, recalling from dynamics, but really is kinematics to be accurate. Okay? You know that the velocity is equal to what? Will be dx dt, no? Now, what is the acceleration? The acceleration is the derivative of dv dt, but also this could be the second derivative of x with respect to t squared. Okay? And in vibrations, and as you have seen in other classes, the derivative with respect to time is indicated by little dots on top of the variable. Okay? So if you want over here, the little dots here indicate this. All right? Okay. So with this new notation, so that we have the equation minus kx equal to ma. Actually, we can rewrite it as minus kx equal to m x double dot, or we can just write the differential equation mx double dot plus kx equal to 0. Okay, so this is the most general form for the equation of motion of the mass spring oscillator. Okay, but here we are in a class called vibrations. So what happens a bit in vibrations here over here? Or you can rewrite this as what? As x double dot. So basically what I'm doing is divided by m plus k over m x equals 0. Okay, but that one doesn't give anything. All right. What's interesting here is that if we rewrite this one as x double dot plus omega sub n squared x equal to 0, where omega sub n is the square root of k over m. So now All right, so in this equation here, what's important to realize is that what is omega sub n? The little sub n stands for natural, and the omega is generally the notation used to specify the frequency. So it's the natural frequency. So basically, physically, what is that indicating? Is that if we move this mass a little bit to the right and let it go with no friction, this is going to start to move back and forth, okay? And the oxidation is going to happen at a certain frequency, okay? Does that make sense? So the frequency of oxidation will be given by the ratio of the square root of the stiffness divided by the mass. All right? Okay, so let's look here. I don't have much space, but you can trust me, the units over here should be what? Should be radians per second. I will give more details when we go to the solution about all this stuff, okay? But so far, the important part is that you understand the physical implication, is that this K over M is the frequency of oxidation, which the one is going to go, no? The higher the frequency means the faster it's going to move. The lower the frequency, the slower it's going to move right and left. Okay? Okay, so let's do a little problem now. So the exercise is to determine the equation of motion. Or if you want, determine the differential equation representing the equation of motion. Okay, so a very similar problem, but this one carries something specific to it, okay? But it's very similar to the one before. So this time, the only thing I'm doing is that I'm moving my one degree of freedom oscillator upside down. Okay, so this will be M. And again, this will be K. So now here what happens is that before we decide to either pull this down or pull it up, the spring at t equals 0 is not on stretch. In this time, the spring is stretched at t equals 0, no? Okay, when the system is not in motion, so let's say K here is stretch at t equals 0. All right? Okay, so doesn't matter, okay? We follow the procedure in order to define the equation of motion. So to find the equation of motion, we need to do two steps. What is the first step? To do the figure or free body diagram, no? Some type of sketch. So we're going to do the same thing as before. We're going to do one for the summation of forces. We're going to do another one for the inertia effects. Okay, this will be, do I need to say that CG stands for center of gravity? Probably you know that, okay? Okay, so initially, what do we have over here? We're gonna have, if we look at the forces, we're gonna have the gravitational force, correct? And then we're gonna have the force of the spring that is holding it, no? A spring equal kx. Now, the important part that I don't know if I did before, yes, I did it before, we need to determine the current system. So in this case, let's say our current system, I mean, it's up to you, you can do it up or down. Here, select to make it down. If you do it up, it doesn't matter, you're gonna get exactly the same equation because it doesn't matter if initially you pull it out and you let it go or you compress it and let it go, no? The frequency of oscillation should be the same. So this should be about the external forces. Now, what will be the inertia effect? Will be here, MA, but we know that MA, we can rewrite it as mx double dot because A, the acceleration is equal to second derivative of x with respect to t. All right, so we do step 2. What type of motion is this object going to have? Translation. Meaning that we need to take summation of forces equals to MA as the basic equation, fundamental equation to derive the equation of motion. So again, equation comes from the figure, no? There is no magic to write down the equation without a figure. All right, so now I look at it, and with this reference frame, what do I get? Minus kx, no? Because we select x positive going down, plus mg will be equal to ma, but we say ma, you can write it as mx double dot. All right, so here I can just rewrite this equation as mx double dot plus kx equal to mg. Okay, so over here, maybe I forgot to mention something over here that you might remember or not from differential equations, but what type of differential equation is this? This is a second order differential equation, but that's not the important part. It's very simple to resolve. The important part over here is that the right-hand side is equal to 0, which means that this equation is said to be homogeneous, okay? So in this case, what is the difference between this equation and this equation? Is that this one has the mg, so it's not homogeneous. So when the equation is not homogeneous, it involves a bit more steps in order to solve. But we don't want to do that because what we try to do is try to learn a procedure that will work every single time. Okay? So the goal now is to make this equation here, to write it under the homogeneous form. Okay? So let's see how we do it, and then let's see what does that mean physically. All right, so, or I can just rewrite this equation here as, let's just do it again, as x double dot plus k over x equal to g, which gives you x double dot plus omega n squared x equal to g, where omega n is the same as before, is equal to the square root of k over m. Let's call this equation here letter A. Sorry, doesn't matter. All right, let's call this one letter B, and that's it. Okay, so the idea over here will be to rewrite this equation, which is not homogeneous, under the homogeneous form. Okay? Okay, so to rewrite and make it homogeneous, what we're going to do is that we're going to rewrite the equation of motion from, let's say, an equilibrium point. Okay? So let's put over here. Now, the objective is to rewrite the non-homogeneous differential equation of motion. Okay, which will be, let's select this one here, the x double dot plus k over m x equal to g. So it's not homogeneous because the right hand side is not equal to 0. Okay, so the objective is to rewrite the non-homogeneous differential equation of motion as an homogeneous differential equation. Okay, so in order to do that, what we're going to do is rewrite the equation of motion in function of the position of the block M at the equilibrium position. So that might sound complicated, but as soon as we do it, you will see it's pretty simple. So let's say at equilibrium position, so equilibrium means this is not moving, okay? So if you do this part will be 0, no? It's like solving a static problem. So the same as before, we're gonna have the force of the spring here, okay, X. And here we're gonna have mx, but the only thing is that we're gonna call this one x equilibrium. That would be the difference. Okay? So in this case, this is an equilibrium. So you see, we follow the same step again. Step 1, we do the figure. Step 2, we're gonna write down the equation, but this time, what is the equation? This is an equilibrium, so that means that we have summation of forces equals to 0, because A will be 0, no? All right? So this is not moving, what do we have? Okay, and again, we need to specify the coordinate system, so it will be the x, okay, or the x equilibrium. We will have minus k x equilibrium plus mg equal to 0. Or solving, we'll find the x equilibrium will be equal to what? Will be equal to mg over k. All right? Okay, so now comes the trick. That is, let us introduce the new variable, and let's call it x, whatever you want to call it, squishy bar on top. Okay, you can call it whatever you want. But this one, that new variables, is the one that measures the motion of spring mass oscillator relative to the equilibrium position. Okay, so over here, the way this variable is related is that x, so what we have would be x is a normal variable now that we had initially. If we do it from the initial position, we need to subtract what was an initial position. So this really becomes x minus mg over k. Okay, let's call this one equation C. Okay, so now what we're going to do, we can do either with A or C, but let's say we're going to use this one. So let us combine this equation with this equation here, okay? Actually, we should do better to use this one, but I mean, we give me one more line. So combining equations, let's say B and C, what do we have? So equation B was x double dot plus omega n squared equal to G, or actually this equation is equal to x double dot plus, oops, I forgot an x here, sorry guys, there's an x over here, plus k over mx, just rewriting this equation here, equal to G, okay? Now, from C, from equation C, what can I say? I can say that x will be equal to what? Will be equal to the x with a squiddy on top plus mg over k. Okay, so all right, since I run out of space, I was gonna do it a bit faster, but all right, page 5. All right, so basically now what I'm going to do is substitute into this equation over here. Okay, so all right, so let me just do this. So continuation of this equation. So we have x double dot plus k over x equal to g. We know this is the same. This is not really the way I wanted to do it, but since I run out of space, this is the same as d second derivative of x dt squared plus k over x equal to g. Now, if I use this relation here, this will be equal to what? Will be second derivative with respect to time of what? X wiggly plus mg over k. Yeah, I'm just substituting the x plus k over m x, which is x wiggly plus mg over k equal to g. So now you know that the mg over k is a constant. Okay, so if you take the derivative of a constant, that is 0. Okay, so read this first term should give you second derivative of x wiggly dt squared plus what? K over m x wiggly plus g equal to g. So now you see what is going to happen is that these 2g are going to cancel, and we end up again now with the equation of motion, but this time the right hand side will be 0, so the equation will be homogeneous. Okay, so we're going to get here second derivative of the wiggly x dt squared plus k over m x dot equal to 0. So now this is homogeneous and is of the same form that we had at the beginning. We said the general form for this equation of motion should be of this form, no? Or this one. All right? So now okay, or this one could be written as what? So this is going to be crazy notation now, because if we use the same notation as before, what should this be? Should be x wiggly sad x, I don't know, or weird x, you know? All right, so dash plus omega n squared x wiggly equal to 0, where omega n is equal to the square root of k over n. All right. So we're going to do another example, or another, how did I call this one? Example or exercise? Yeah, I call it exercise. We're going to do another exercise over here. And again, it's going to be to determine the equation of motion. So far we have only studied translation. So this example is just to show the rotation, okay? All right, so in this case, we're gonna have, let's say 1 bar. Or 1 link, okay? So there's a link over here. So again, imagine you have a bar that if it was in equilibrium, it would just be straight down, no? But if you move it from one side and they say there's no friction at the link, if you let it go, this should oscillate forever that way, okay? Like if I take this marker, this could be doing this way forever, no? All right. So let's say over here that this, you move at an angle theta. So instead of x, you can have theta. Let's call this point over here point O at the hinge. Let's say the bar has a mass m. This should be the CG and a length L. So L is length of bar. Okay, so let's derive the equation of motion. So in order to derive the equation of motion, again, we need to follow the 2 steps. First step, do a figure or figure diagram, and then write down the appropriate second law and write down the equation. All right, so step 1, to do the figure. And again, I'm going to do 2 because you have, okay, they should be identical. They're not identical, but not a big deal. From the CG. So let's see, what would be the forces acting over here on the bar? So we have the weight, gravity, and then if we remove the link over here, we'll have some O sub y, O sub x, no? Some 2 reactions at the pin. Anything else? I think that's about it. And then what type of motion is this going to have? Let's say we move it to the right. This is going to move. I mean, it doesn't matter. It's going to move that way, but let me just do it this way because this is a normal sign convention. Remember, for the notation, is positive is counterclockwise, no? Yeah. So you will have what? I, and this is interesting here. alpha. So let's see. Over here, let's stop for a second. Because now this is an important part. And I'm not going to go into much detail. This should be statics, dynamic, sorry. So what is alpha? Alpha, by definition, is the angular acceleration. And what is theta in this problem? I think I have it here, but I'll remove it. What is this theta over here? Theta is just the angle of deformation or displacement angle. Okay, so the same thing as before that we had for translation. The velocity of translation is equal to what? dx dt, no? All right. Do we have something called angular velocity? Yes. What is the letter used for that? That is omega, no? Is equal to what? d theta dt, this being the angular velocity, and alpha is what? Is d omega dt, but this is also what? The second derivative of theta dt. Okay? And if we use the same notation as before, we could write this as theta double dot. So basically, the important part over here is to realize what? What type of motion is this bar really having? Is rotation. So if it has rotation, we're going to have to use the rotation terms. Angular acceleration, angle of deformation, all right? And then what will be the equation? What will be the dynamic equation defining the motion of the rotation? So step 2, maybe I'm going to add one more thing over here, but I'm going to do it after I rewrite this. What is the equation defining the rotation? Summation of moments equals to I alpha. Okay. All right, I want to finish this problem. So something very careful here. You need to be very careful. In this equation here, what is I? I is the moment of inertia. Okay, I'm going to give you a definition. What does it mean physically? Physically, the moment of inertia represents the resistance of this bar to rotation. Okay? So it means the resistance of this bar to rotation. How unlikely it is to rotate. All right? So now, something even more important is that when you take the moment equation, you need to take the moment always about 1 point, no? Okay? So this point here, and when you take the moment of inertia, you also need to take it with respect to 1 point, no? So make sure that this one is always the same point from where you take the equation. All right? So, for instance, maybe I'm giving too much information here, but the moment of inertia, this is given to you, okay? I'm not going to ask you to calculate. The moment of inertia of a bar from the CG, maybe you remember that from dynamics, is equal to what? Is m L squared over 12. But if you do it from one of the ends, so A or A prime, just going to call it using the parallel access theorem, okay, I cannot review everything. this is equal to ml squared over 3. Okay? So in this problem over here, what is the simple case? This is really rotating about which point? About point, oh no, the length. Okay, so let's say over here, let's rewrite the equation as doing summation of moments about point O equals to I sub O alpha. All right, so let me add some stuff to the figure. This will be L over 2, this will be L over 2, no? All right. Okay. So now, if we take moments about point O, what would be the moment created by the force mg? So the other things, let's say, is always positive going counterclockwise. This is the normal sign convention. So the moment created by mg, is it positive or negative? Is it going to make it go clockwise or counterclockwise? It's going to make it go clockwise, no? So it should be negative. So you know moment is force. So mg is the force. What would be the arm? The arm should be this horizontal distance. That horizontal distance would be equal to what? L over 2, and if trigonometry should be sine theta. Okay? And that should be equal to what? So in this case, we move it up. We can leave it that way, actually. Let's just forget about. So now the right hand side should be equal to what? I sub naught alpha. Okay? But what do we know about the alpha over here? That is equal to the theta double naught. So very quick, I can just rewrite this as I sub naught theta double dot plus mg L over 2 sine theta equal to 0. Okay? And we know that I sub naught is m L squared over 3 All right, so let's go still have for minutes. So this should be equal to m L squared over 3 theta double dot plus mg L over 2 sine theta equal to 0. So if I divide by m L squared over 3, I get theta double dot plus what? So the m will disappear. One of the L's will disappear. So we have, and this will go on, we have 3 over 2. No, 3 over 2 G, the M disappears, over L sine theta equal to 0. Now I'm going to be quick now, but I just want to make sure I finish. Two or three more lines, I'll be done. Okay, so using the small angles assumption, which you do that all the time. What is the small angle assumption? Is that if you have a very small angle, think about a circle. If the angle is very small, cosine theta should be equal to what? 1, no? And for very small angles, you say that sin theta is approximately equal to theta. So that in that case, we have the equation theta double dot plus 3/2 g over L sine theta equal to 0. That becomes theta double dot plus 3/2 g over L theta equal to 0, or theta double dot plus omega theta square theta equal to 0, where omega square theta will be equal to the square root of (3g) or 3/2 of g over L. So in this case, what would this be? This would be the natural frequency of oscillation, okay? So the other one was K over M was in that direction. This one will be in this direction for the bar. But what's important over here to observe, and I will finish with that, is that the form of the differential equation that we had from page 2 is what? Omega x double dot plus omega n squared x equal to 0. Now, even if it's rotation, the form of the equation, differential equation, is the same, no? What changes is the variable. So basically, what's important over here to understand is that we are leading all the time about finding out that the form of the differential equation can always be rewritten under this form, okay? And then we need to learn how to solve it. Okay, that's it for today. Yes?
Should I just be the omega